There's the chief. There's nothing. Okay, well, here's a different, maybe it's connected to this. No, you're getting slide. Okay. Well, oh, that was the wrong thing. Okay. Yeah, I guess so. Because maybe it's impossible to come in. Aha. Can you remind me of your name, please? Robin Pollard. Robin Pollard. Good, good. And you're a student of Angela? Angela, yeah. Really, at Cornwall? In California. Right. I'm also working on liquid crystal elastomer. Good. You're nice. Good. I think this is that, except for the Roscoe. Then I don't know how to Zoom part. There is there should be some instructions on that. There's a post-it here that says Zoom details. I guess I can just. Start Zoom. Probably. Yeah. There is Zoom going on. Yeah. I think. Like in this laptop. Oh, okay. Zoom is going on. They will point to my screen. I don't know. So you're back at the screen. You're leaving next week, right? Or like and you're coming back then. Okay, so how long I click on? Okay, so then we should probably have you give a talk after the workshop. Yeah. Yes. Because we are kind of completely booked for next week. Yeah. Yeah. So you need to log in.
That's the Zoom, yeah. Just, we just only got the Zoom details there. It's not with these ones. The Zoom details. So you have to type those in. Yeah.
Russell, can you start me to raise? Yeah. Oh, yes. Do I want audio from my computer? Just audio.
Sorry?
Do I want to join with what?
Yes.
Yeah.
You'll be back to doing it from home, so the same.
Unmute USB.
One of these causes echo. Yeah.
Oh, okay, so you stop that.
Yes, thank you very much.
Yes, I received it, and I'll go through the latest updates. It's great, it's wonderful first. So.
Yeah. Thank you. Ready? Sorry.
Yeah, yes, it's like that. I'm around today, and I tomorrow.
Maybe tomorrow they need to be moved.
Perfect. No, thank you.
Anyway.
Yeah. Oh, you don't know the
I
close.
think we want to be on open. Yeah, you still more, I think, but of course, actually, attached to the door, so you can find it.
I see one of those, yes.
Yeah, you can keep them up and down.
Sorry. Thank you. That's not good. But you're the on this computer. Somebody can see it. So we need to go and get the. Get the.
Any?
Yeah, there's some issues with Buddha was connecting to Zoom and it says trying to.
And a lot of this is family. And we just visited there, we saw the town, careful about sliding. No, thank you. The two breakfast. Another opportunities. Exactly. Now it's fine.
On the astronomy, it's absolutely vast. Yeah.
Just, yeah, in particular, even just this one time. And adding some persistence, that's possible.
Oh, what did I hear?
I'm sitting here, that seems to be fun, take next.
She was trying to connect remotely and it just.
Yeah, so this one was actually trying to on YouTube.
Yeah, but then checking the video, apparently it's working. Okay, so can we get started?
I just feel that what's like was.
Yeah, because they have some issues with streaming with you. If you log in to Zoom.
Oh, yeah.
I just was like reading the news. And she says, I saw it. And it's Jonathan has a stepsister. She married someone in Hawaii. They divorced. So not in the still my business.
Okay, so shall we get started? Sorry about the delay. The apparently a YouTube link is not working, Zoom link is working. So we have two talks today. So first Jonathan Selinger and then Wilson Poon in the afternoon 3 o'clock this room. And then schedule for the next week is going to be shared later today. Yours.
Thank you, Roscoe. Okay, so in the last few years, I've been working on a reformulation of elasticity theory, the Frank saying elastic free energy for liquid crystals, which is mathematically equivalent, but I think provides different kinds of insights into it. And then it turns out that the same style of reformulation also works for the Helfrich free energy for lipid membranes. And so those are the things that I wanted to kind of present to you guys today. Let's see. So I made a okay, so I've got this.
Probably escape and go again, that's all. Goes from, yeah.
Okay.
Again,
Let's try that again. All right.
yeah.
Okay. Now, it's just a little bit of the okay. I've got my mini introductions with crystals. Does anybody want mini introductions to liquid crystals? Phases with partial order, more than liquids, less than crystals. They've got these long organic molecules like this. On a coarse-grained level, we can represent them as if they are just arrows with some orientation. And then we've got a lot of them, like 10 to the 23rd, some sample. And they form a phase with orientational order, right? And the orientational order is similar to a ferromagnet, but not the same as a ferromagnet, because a ferromagnet would be pointing in one direction. And here it's pointing 50-50 backwards and forwards along some axis. And so we could represent that as a double-headed arrow like this, right? And then if we zoom out, and this thing is called a pneumatic liquid crystal phase. It's the most common type of liquid crystal phase. And the double-headed arrow is represented by a unit vector n hat, with the understanding that n hat and negative n hat represent the same physical state. Then we can zoom out more and say, in this region, our orientational order is aligned along this axis, but over long length scales, there's a variation in which way it's pointing. Right? And when you have a variation like that, then the gradients of the director cost some amount of elastic free energy. Right? And that's what this talk is about. How much elastic free energy do they cost? So we've got this director field, N of R. Okay, so to make an elastic free energy, what we want to do is to expand the free energy up to quadratic order in first derivatives of N. Okay, so to say that each first derivative represents some variation of N as a function of position. And so the first derivative squared makes an elastic energy constant. So as our first simplest approximation, we could assume that there's the same free energy cost for all gradients of the derivative. Okay, so that makes this expression for the free energy, which is implicitly summed over the indices I and J. Okay, so this means the derivative of nx with respect to x squared plus the derivative of x with respect to y squared, etc. Okay, and all of these things are multiplied by a single elastic constant k. Right? This is sometimes called the single Frank constant approximation, or sometimes called isotropic elasticity for the liquid crystal. It's a reasonable first approximation. It's not bad, but it's not good enough for designing liquid crystal displays. The limitation is that there are different kinds of director gradients, and the different kinds of gradients cost different amounts of elastic free energy. And so the amount of free energy depends on the relative orientation of the director and the gradient direction. Okay, so in the theory of magnetism, people call this spin orbit coupling, right? That is, that the magnetic spin lives in the same three-dimensional space as the director gradients, as the gradient directions, as the X, Y, and Z. Right? So this expression doesn't know about that, right? That the gradient index is summed with the gradient index, and the director index is summed with the director index, right? So this would work even if they lived in completely different spaces, spaces of different dimensionality, right? But in real life, it's the same three-dimensional space. Okay, and so those things are coupled together. So we need a full Osane-Frank free energy to classify the different kinds of director gradients so that we can say how much free energy is associated with each kind of gradient. There's a standard version of how to do that, which has been around for 60 years. And then I'm proposing a little variation on that. That's what I want to show you today. All right. So to show you my version, let's suppose to begin with that the director is approximately in the z direction. Okay, so that it is one in the z direction and then these small variations in the x and y direction. This approximation is not necessary. I'm going to go beyond it later, but this is just by way of introduction. So in this situation, we could construct a tensor of all the possible director gradients, and there are 6 of them, right? There's nothing in the last column because the n sub z is approximately constant. Okay, so I want now to break up these 6 components based on how they transform under rotations about the director itself. Okay, so how they transform under rotations about z, that's director orientation. Okay, so in mathematical language, you could say I'm looking for the irreducible representations of the group of rotations about z. All right, so one representation, one kind of mathematical object that is special all by itself is this pair of components, okay? So the derivative of an x with respect to z and the derivative of n y with respect to z, right? This set of components is called bin, okay? And so it represents how these transverse components of n are varying in the n direction, right? Which is here approximately the z direction. Okay, so that's a variation which looks like that, right? Or for an interpretive dance, right? I could do a variation like this, or a variation like this. Okay, and so that is a 2-component vector, a vector in the xy plane, perpendicular to the average n. Okay, and if I rotate about z, then this transforms into this. Okay, and it doesn't transform into anything else. So this is what it looks like to have a variation which is locally pure band and nothing else, none of these other derivatives. Okay. So here I've accounted for 2 of the 6 components, 4 to go. Now, what remains is this 2 by 2 block of the tensor. Okay. As a first step, I can break that 2 by 2 block into symmetric and anti-symmetric components. And I'll just look at the anti-symmetric component. Okay. The anti-symmetric component is this simple tensor times this combination of derivatives. Okay. So this combination of derivatives is something special. And in the liquid crystal literature, this is called twist. Okay. So you can see that this is a pseudo-scalar that is under proper rotations about the axis. It transforms into itself, not into anything else. Under reflections, it changes sign. So that makes it a pseudo-scalar. And this is a picture of what it looks like, right? So this is a picture of a variation that has locally pure twist and 0 of everything else, right? So it's a variation on my interpretive dance. It looks like this, okay? And it's the same going all around. it has to be the same going all around because it's a scalar. It doesn't have any direction other than n itself, right? And so it has to be the same going all around. Right? Liquid crystal people sometimes call this double twist. I am claiming that double twist is pure twist. I will talk about cholesteric later. Okay, this then accounts for one more of the 6 components. 3 done, 3 to go. Now, what remains is a symmetric tensor, this 2 by 2 block. Right? I can now break that into its trace and a traceless part. Let's look at the trace. Okay? That makes this combination of derivatives. That is called split, okay, in the crystal literature. And it is a scalar, right? It transforms into itself under rotation. It is a proper scalar because it does not change sign for reflection. And it looks like this. Okay, so it's a variation where the director is tipping outwards as you go away from the center. And it is also the same as you go all the way around, which it has to be because it's also a scalar. Okay, so it looks like an ice cream cone, not like a slice of pizza. You might call it double splay by analogy with double twist. No one other than me actually calls it that, but it's good. Okay. So that is scalar is 1 degree of freedom. Right? So I've now accounted for 4 of the 6 degrees of freedom. 2 to go. The 2 remaining things are the symmetric traceless tensor in this 2 by 2 block. Okay, so there's one component which is the XX component, and another is the XY. Okay, this is a deformation which looks like that. Okay. So this is a locally pure picture of this kind of deformation. Okay, so one component of it is going outwards this way and inwards this way, 90 degrees. Okay. The other component of it is rotated by 45 degrees. So it goes outwards this way and inwards this way. Okay. When you rotate by a full 90, you're back to the negative of the first. So this is the 4th mode of liquid crystal deformation. And it has 2 components as a symmetric, traceless, 2-dimensional tensor should. It doesn't really have a name. And I have, to my embarrassment, I've been kind of inconsistent in what I have called it. So in one paper, I called it biaxial splay because it's different in the 2 directions perpendicular to the director. In another paper, I called it tetrahedral splay because it kind of resembles a tetrahedron standing on one edge. You can see with this red little outline that's embedded in the structure. And here it's rotated by 45 degrees. But lately, I have just been calling it the delta mode. The same decomposition of the director gradients works in general, right? It doesn't depend on the assumption that I made that the director is approximately in the z direction, but it works in general. Here is a general expression for the decomposition in terms of bend, twist, splay, and this delta mode. So bend, has a vector construction. You could write it as n cross curl n. That's how it's been written for 60 years now. Twist is dot curl n. Splay is the divergence of n. Delta, well, it's everything else, right? It's this thing minus that, right? So it's kind of messy, but it's certainly not the worst thing I've ever worked with in my career. And you know, I've got some nice mathematical code that talk to 86. This construction was done a few years before me by these guys in the UK, Tom Michon and Gareth Alexander, in a paper about umbilic lines in orientational order from 2016. As far as I know, they were the first to develop this decomposition. And they did it for the purposes of topology. I'm now using it for the purpose of elasticity theory. For elasticity theory, we want to, we've seen that there are these four kinds of director gradients. Each of them has to cost some amount of free energy with its own elastic coefficient. Right? There's no symmetry reason why those elastic coefficients have to be the same. Right? So we think that there should be a free energy density, which should be something times splay squared plus something times twist squared plus something times bend squared plus something times delta squared. Reasonable. Now, what should we call these coefficients, the dots here in this expression? In order to be backward compatible, let's compare this with the standard version of Oseen-Frank free energy that people have been using for all these years. Okay. The standard version looks like this, okay? That it is a constant K11 times splay squared, K22 times twist squared, K33 times bend squared. And then people haven't been talking about this delta mode. Instead, for all these years, they said there's a negative K24 times the divergence of all this mess. And the divergence of all this mess is called saddle span. Okay, and so this has been a part of the liquid crystal literature for many years. Okay. And so now, if I use the construction on this slide to simplify the mess in saddle splay, it turns out to be equal to a half splay squared plus a half twist squared minus the trace of deltas. Okay. So if I put that into this equation, it becomes this form. Okay. So something times splay squared, and the something is K11 minus K12. Likewise, the thing multiplying twist squared is K22 minus K24. The thing multiplying bend squared is K33, and the thing multiplying delta squared is K24. Okay. So I'm going to stick with these coefficient labels to be compatible with literature. But I maintain that this is what an elastic free energy ought to look like as the sum of squares of things, as opposed to this other more complicated non-square-ish kind of expression. So that's consistent with this argument. Now, in analyzing the K24 term, there are many years of literature in which people use the divergence theorem. Right, and so they take this expression, which is a divergence integrated over the interior of a sample, and transform it into a surface term, and say this is a kind of surface elasticity. Yes, you are free to do that mathematically. I just don't want to do that. Okay, I choose not to do that. I choose to keep everything in the bulk and analyze it in this way. Okay, and I've written an article where I go through a whole bunch of classic problems that have been studied in terms of the surface elasticity And I think they can just be analyzed more easily in terms of bulk elasticity in this language. But the surface expression is not wrong. I mean, it's mathematically equivalent, can transform one into the other. And so the mathematical predictions are the same, but they're just expressed in a different way. And I will tell you one example coming up later. As far as comparing with this simple approximation that I showed you earlier, right? This simple story can be expressed in terms of splay, twist, bend, and delta in this way. Okay, so it corresponds to K11 equals K22 equals K233 equals 2 times K24 that equals a single elastic constant. And so this is what's called the equal frame constant approximation. So this is my ideology about liquid crystals. Now, let me show you what this means for lipid membranes. Okay, are there any questions before I go on? Good.
Jonathan, the sign of this, because it's written in the difference of K11 and K4. I understand that in this approximation is just going to give what it, but can it sign, and if it does, then does that need to be
Yeah, so let's forget about this approximation and go back to the full form, right? For a nice, well-behaved elasticity theory, right? You would want all of the coefficients to be positive, right? So that this free energy would be manifestly positive. Okay? So therefore, you would want K11 to be greater than K24 and K22 to be greater than K24. Okay. This actually exists in the literature already, these statements, and they're called the Erickson inequality. Okay, so it's something that Erickson analyzed. It was a hard problem for Erickson back these many decades ago because he was working with this other notation there, right? Expressed in terms of this notation, the Erickson inequalities are kind of trivial. Right, that it's just looking at these coefficients and saying that they're positive. That is true in normal liquid crystals. Right? Weirdly, there is an experimental system where the Erickson inequality on K22 and K24 is violated. Right? That is the system of lytropic harmonic crystals. Right? And people do find that if you put lytropic harmonic liquid crystals into a narrow cylindrical tube, that they spontaneously form double twists, which can be randomly right-handed or left-handed. And so that is a situation where this inequality is violated. Okay, and so the coefficient of twist squared is negative, as shows up experimentally. So you might ask, what keeps the free energy from going to negative infinity in that situation? Two possible answers to that question. One has to do with compatibility considerations that I will talk about later, that the compatibility prevents the twist from getting arbitrarily large without these other things getting large. Right? The other possibility is maybe there are higher order terms. I've worked on this and argued for the compatibility story, and Epifanio Virga, who you might know, has also recently worked on this and he's argued for that higher order terms. Okay.
So could you write it in terms of adding a spontaneous?
In terms of, say again?
A spontaneous twist, so that you have preferred twist in this case.
Yeah, but it could be positive or negative. And so there was a spontaneous symmetry, right? That makes it positive. Amira?
Find out the surface there and one.
Divergence theorem says they're the same, right? I mean, the divergence theorem says you have a bulk integral which equals a surface integral. And the divergence theorem is just a mathematical statement. It doesn't say anything about how to understand the physics. All right, and so, right. Well, I mean, I think physically, it's a bulk story. I think that the transforming it to a surface term is mathematically correct as long as there's nothing happening inside the bulk that violates the theorem. So for example, if there were defects inside the bulk, those would mess up the surface analysis. People get around that by saying the defects are like internal surfaces. But even if there's a temperature gradient in the bulk, this is something that I learned from Ralph Stenarius. But if there's a temperature gradient in the bulk, so that the surface is all at one temperature, but somewhere in the bulk, there's a different temperature, right? That messes up the transformation of things to the surface elasticity, right? That the K24 term changes just in response to the temperature inside, even if there's no change of anything happening at the surface, right? And so I'm on team bulk all the way.
And there are no weird wrinkles in the divergence theory when you have an orientation vector field where +1 is equal to -1.
If there are no defects in the sample, then you can make a single choice of n everywhere in the interior, right? And so you only have to worry about the equivalence of +n and -n if there are defects somewhere in the sample, and then you have an even bigger problem. Like, want to lipid membranes? For lipid membranes, okay, so this is another classic problem in the literature, right? What's the elastic energy of a curved lipid membrane, right? And this is what's addressed by the Helfrich free energy, or people use other names. I don't know the history. People who do know the history associate it with various other names in addition to Helfrich, okay? I'll just say Helfrich. In the Helfrich range, we say there's a curvature test of the lipid membrane. Curvature is what costs free energy. So let me try to analyze that problem in the same style as what I just did for the director field. Okay, so you have a curvature tensor, which is a two-dimensional tensor of rank 2, that symmetric. So it has these 3 degrees of freedom. If the membrane is approximately flat, then the tensor could be expressed in terms of these derivatives of the height function. But that is not necessary for any arbitrary membrane, some symmetric 2 by 2 at any particular position. Let me analyze it in the same style as what I did for the director gradient tensor. In this situation, there's no derivatives along the z direction, so nothing like bend, forget about it. There's no anti-symmetric, so nothing like twist, forget about twist. But I can still take this and break it up into a trace and a traceless part. So in the principal component system, the eigenframe of the curvature tensor, right? It looks like a 1 over R1 and 1 over R2, right? Where R1 and R2 are the 2 principal radii of curvature. So the trace looks like this, right? It's just the sum of those 2 principal curvatures. And the traceless part involves the difference of the 2 principal curvatures. So the trace, of course, is 1 degree of freedom. The traceless part, well, in the eigenframe, it's 1 degree of freedom, but in an arbitrary frame, it has a magnitude and a direction, right? Or I could just take this thing and subtract off the trace of that. And so it has an XX component and an XY component. Right? So the trace is on display, right? And it has 1 degree of freedom. The traceless part is like the delta mode. It has 2 degrees of freedom. And so that accounts for the 3 degrees of freedom in a symmetric 2x2 matrix. Okay. So the free energy density should be something times display squared plus something times delta squared, right? Or if I translate that into this language, it should be something times the curvature sum squared plus something times the curvature difference squared. Is that the same thing as the Helfrich free energy? Yes, as I can demonstrate using some nice high school algebra right here, right? If I just expand that stuff, it turns into K11 times this sum of curvatures squared minus a K24 times the product, okay? So the sum of these curvatures is the 2 times the mean curvature, commonly called H, okay? The product is the Gaussian curvature. And so this becomes equivalent to the standard expression for the Helfrich free energy, which involves the mean curvature squared and the Gaussian curvature. Okay. The Gaussian curvature also satisfies theorems the same as the saddle splay does in the liquid crystal context. That is, you can integrate it to some surface thing, right? Or if you integrate over a closed surface, it integrates to a topological invariant related to the genus of surface. So that is a transformation that we are free to make if we want to, but maybe I don't want to, right? Maybe just for the sake of discussion, I want to keep everything in the bulk. And then by analogy with the liquid crystal problem, I could work out elasticity in terms of the curvature sum and the curvature difference as 2 fundamental elastic modes of the liquid membrane.
Yeah, sorry, can you still apply the Ericsson inequality that K11 should be larger than K24, so that means
yes, that is correct, yes. And so if that inequality were violated, then the system would be unstable unless it stabilized either by a compatibility constraint, which would say, this can't get arbitrarily big, this can be big.
So that also means in the Helfrich free energy kappa is not kappa black.
I guess that's right. That's probably been studied a lot, but I can't remember. Maybe somebody here. But I know I remember seeing somewhere in the. Okay, so the summary so far. That for liquid crystals, I want to work in terms of 4 elastic modes. Okay, the standard, bend, twist, and splay. And then this delta mode, which is related to saddle splay, the ways I showed you. For lipid membranes, I want to work in terms of 2 elastic modes. So forget about bend and twist, but splay turns into this curvature sum, and delta turns into the curvature difference. Sum is isotropic, it has 1 degree of freedom. The curvature difference has 2 degrees of freedom. So you can interpret that as a magnitude direction. Okay, so it's like if there's a satellite shape, then you could say, what's the magnitude of the satellite shape? And what's the direction? Which way is the saddle pointing in the two-dimensional? Right. Okay, so why do I care about this? Okay, there's several reasons for liquid crystals, okay, but the main reason that I want to emphasize here is that there are situations where liquid crystals can have favorable director deformations, and this provides a way to analyze those things, okay? And I will argue there could be similar considerations for liquid mirrors. Let's deal with the liquid crystals first, because I've done more work with that. Suppose you have a system with some extra molecular order in addition to the normal pneumatic. So, for example, suppose you have banana-shaped molecules, right? And they have a spontaneous tendency to align the banana axes, right? So that, they might be randomized in a uniaxial pneumatic phase like this, or maybe they're aligned with each other, okay? So suppose for some reason that the energy favors alignment of the banana directions, right? In that situation, we could add an extra term to the free energy, which is the bend dotted with this perpendicular polar order, perpendicular to the director itself, right? That would be allowed by symmetry because these things are both vectors in the plane perpendicular to the director, okay? And then if we minimize over bend, splay, twist, delta, if they are independent, then we would say there's some ideal local state which has non-zero bend, zero splay, zero twist, zero delta. Okay? So that would be a liquid crystal that wants to bend. Right? And this is called the flexoelectric, converse flexoelectric. And it's been established experiment. Likewise with splay, if you have molecules that look like pairs, then if you have a population imbalance, so more pairs are pointing up than down or vice versa, then that makes polar order parallel to the director. And you could add a term to the free energy, which is this splay times n dotted into this parallel polar order. And then the ground state of the free energy has non-zero splay, right? It tends to come around like that. Like that's again out of the screen. And so the ideal local state is non-zero splay, zero bend, zero twist. Likewise with twist. This is what liquid crystal chemists do all the time, right? If they make molecules that are different from their mirror images, and they have an enantiomeric excess, right? More right-handed and fewer left-handed or vice versa, then there's some chiral order parameter which couples to the twist. And that tends to favor a non-zero twist. But then there's still zero bend, zero splay, zero comes. And in principle, that could be true also with my delta mode, right? If you have molecules shaped like these distorted tetrahedra and they are aligned in the XY plane, then there'll be an ideal local state that tends to tip outwards like that. It's like that to have this delta mode. Okay, so that's what the liquid crystal wants to do. But can it do the thing that it wants to do? That is it possible to make a director field with the ideal state that has one of these things, constant and non-zero, and the other three all zero? Not just at one position, but everywhere. And the answer to that question is no, right? That this violates compatibility considerations, like elastic compatibility considerations for those of you who are familiar with solid elasticity, right? So in that analogy, the director is analogous to the displacement field. And these bend, splay, twist, and delta are analogous to the strain tensor. And just as there are compatibility considerations for the strain tensor, there are compatibility considerations for these guys. And there's a whole history of theoretical research on these things, which I maybe don't have time to tell you, but it's been worked on for many years. And I'll highlight the work of Epifanio Virga, who showed that in 3D Euclidean flat space, the only uniform, spatially homogeneous combinations that are allowed are twist and delta or bend, twist, and delta. And that's it, nothing else, right? Other than that, it has to be not spatially homogeneous. This has also been generalized by me and other people to non-Euclidean geometry for anybody who cares about 3D non-Euclidean geometry. So that is the phenomenon of geometric frustration, right? That there is an ideal local state, but it just can't fill up space. So what does the crystal do to minimize its free energy, right? Well, it needs to make a compromise structure, and there are two possibilities. One is to fill space with an allowed combination of deformation modes, a combination of the favored mode that reduces the free energy and some other mode that increases the free energy. Maybe it's worth it to get the favored mode. Alternatively, maybe it can break up space into domains of the favored mode that are separated by domain walls or defects. All right, let me show you an example. Let's think about chirality, because that's the most common situation. So if you have a chiral liquid, it tends to form twists. Argue to you that pure twist means double twist, like that. But it can't fill up space with pure double twist. So what can it do? Well, one possibility, the most common possibility, is to make a cholesteric phase, which looks like this. So this structure is a helix with a helical axis in one direction. Here, just in the z direction. Okay? So that the director going upwards goes around like that. And it's uniform as a function of x and y. So, an equation for that structure is like this: cosine of qz, sine qz, 0. People sometimes speak as if that had pure twist, but that is not really correct in this way of thinking. Okay? This has, I can calculate explicitly, a 0 splay, non-zero twist, 0 bend, non-zero. That's why it's a combination of twist and delta. The twist reduces the free energy. The delta increases the free energy, but not as much. So it's worth it. By comparison, another thing that a liquid crystal, a chiral liquid crystal could do is to make a blue phase. Okay, so a blue phase is a very complicated structure, which I've tried to draw here. It consists of a whole bunch of tubes arranged in a cubic lattice. Okay, so for each tube, the director right in the middle is sort of aligned along the tube axis, and going outwards, you have this double twist, all directions. Okay, and then it tips over by about 45 degrees to the edge of the tube. Okay, and then you can fit together a whole bunch of these tubes with cubic symmetry in a BCC or simple cubic symmetry. And then the director in between the tubes can fill up space almost everywhere, but not quite everywhere. It needs to make defect lines. And so you get a cubic lattice of defect lines, which are indicated by the blue lines here or there. So which is better? Right? How does a chiral liquid crystal decide whether to make a cholesteric phase or a blue phase? Right? Well, in both cases, you have twists everywhere. Okay, and you can have the ideal amount of twist. You can have any amount of twist everywhere. Okay, so people sometimes speak as if the blue phase has more twist. That is not true. The cholesteric phase can have as much twist as you want, just by making the helix tighter and tighter. Right? So that does not distinguish between these phases. Okay, the distinction has to do with what sacrifice does the crystal need to make in order to achieve the twist. In the cholesteric phase, what it does is have this non-zero delta everywhere. Okay, that's the thing that it gives up. In the blue phase, it doesn't have very much delta. It has approximately pure double twist everywhere in these tubes, but it needs to make all these disclinations. All these disclinations that cost disclination core free energy. Right? So you have to ask, which is worse, having the delta free energy or having the disclination core free energy? The delta free energy is proportional to Q24. The disclination core free energy is some extra parameter, okay, which has the same dimensions. So the question is, which of those things is higher? If the core energy is higher, then you make a cholesteric phase. If the K24 is higher, then you make a blue phase. This story that I'm telling you is compatible with a different story that's been around for decades, right? Back in the 80s, early work about blue phases, people used the divergence theory. And they said the K24 energy integrates to the surfaces, and all these disclinations are like internal surfaces. So the K24 integrates to be some surface energy along all the disclinations, and it turns out to be negative. Okay, so they said in the 80s that all these disclinations have some negative energy coming from K24, and that's what stabilizes the blue phase. So the story is not wrong, it's mathematically equivalent to what I'm saying, but the older story is just kind of weird, right? To think of why should there be a negative energy associated with disclinations? And so I would say, for the purpose of storytelling, I like my bulk story better, but mathematically, it leads to exactly the same conclusion of an energy balance between K24 versus the disclination core. How am I doing on time? Not so much. Sorry, 10 minutes. I have similar stories about modulations that are driven by bent systems of bent core crystals. Okay, that makes a twist bend pneumatic phase or a splay bend pneumatic phase, which are things that have been studied in the liquid crystal community over the last 20 years. And so that fits into this general ideology. So I'm going to skip over. If you have parallel polar orbit, so if you have pear-shaped molecules and they tend to align in this way where one end is pointing up and the other end is pointing down, that makes a favorable splay. And the favorable splay could arrange into a lattice separated by defect walls. And this has been something that's been studied in the liquid crystal community for the last 5 years. And so I'm going to skip over that. It sort of also fits this ideology. And then if you have favorable octopolar order, if you have these, funny shaped molecules, and they tend to align with each other, that this is total speculation on my part. This hasn't been studied in the community at all, but I could imagine this making a spontaneous cholesteric phase, because the cholesteric phase includes a lot of the delta deformation. And so you could make a spontaneous cholesteric phase that could be randomly right-handed or left-handed. Or it could make a splenomatic phase with domain walls. These are total speculation. What about for lipid membranes? Let me close with this. All right. What if you have spontaneous polar order? That is, you have a membrane and the two sides of the membrane are different from each other. Okay, so the molecules are tending to align, and the fat ends go to one side of the membrane and the skinny ends go to the other side of the membrane. Or there's a population difference between the populations on the two sides. Okay, and here I've drawn it as sort of a multi-lamellar structure, but one step. Right? Again, that makes a free energy, which looks like the splay squared plus delta squared, and then minus some polar order that couples linearly with the splay. Or if I express it in terms of the principal curvatures, right, then there's something with the curvature sum squared and the curvature difference squared, and then a term that couples linearly to the curvature sum. Or in the classic way of transforming into mean curvature and Gaussian curvature, then there's this mean curvature squared, there's a term proportional Gaussian curvature, and then there's something which is linearly proportional to curvature. This is a part of the standard Helfrich free energy for membranes, and it is called spontaneous curvature. Now, okay. So for all these decades, people who study the elasticity of membranes have thought about this thing, okay, as spontaneous curvature, and it tends to make the membrane not be flat, it curves, okay? So thinking about it in terms of the curvature sum and the curvature difference, we would say the ideal structure has a curvature sum, which is non-zero, a curvature difference, which is 0. And so those two things together imply a sphere, right? That the ideal structure of such a membrane is a sphere with a curvature given by this spontaneous curvature perimeter. So that's great as long as the membrane is free to form a structure with Gaussian curvature. Some membranes can, some membranes can't, right? If they're fluid, they can. If they are solid, then they can't, right? Then that would require prohibitive stretching, compressing the membrane. In that case, a cylinder might be a reasonable compromise structure because it has some zero curvature sum. Now, what if you have molecules that are shaped like these funny things, right? Or at least have some component of their shape, the same symmetry as these objects. In that case, the free energy could involve splay squared and delta squared, and then this delta deformation mode multiplied by an octopolar order parameter, which indicates how well are these funny shaped molecules aligning in the XY plane. Expressed in terms of the principal curvatures, that means something times the curvature sum squared, the curvature difference squared, and then something times the curvature difference to the first power. This is not part of the standard Helfrich free energy. Why not? Because the standard Helfrich free energy is meant to describe membranes that are isotropic in the membrane plane. And if there is octopolar order like this, then the membrane is not isotropic in the membrane plane. Okay, but it could form spontaneously. You know, even if you think you have a membrane that should be isotropic, maybe it makes a local region with this spontaneous octopolar order. And in that case, you would have a linear term in the elasticity coupling to the curvature difference. In that case, the ideal curved structure would have a non-zero curvature difference and a zero curvature sum. Okay? So the ideal local structure then would be some kind of saddle shape. Or perhaps that could be extended over long distances by making a twisted ribbon like this. Okay? So twisted ribbons like this do form in biophysics, and I'm suggesting that this could be a mechanism for stabilizing structures like that, if there is local octopolar order in the membrane. Again, some membranes can form this if they are fluid and free to have Gaussian curvature. Other membranes cannot form this if they are solid, so they can't make Gaussian curvature. So in that case, a cylinder might be a reasonable compromise because it has a non-zero curvature difference. So if you see a cylinder experimentally, you don't know, is it stabilized by this mechanism or is it stabilized by this other mechanism, right? Either way, it could go, you have to look at more details of the experimental system to know what's going on. All right, I'm out of time. So I will summarize my story here. I've re-expressed liquid crystal elasticity in terms of these 4 modes. Each of them might form spontaneously. There might be a ground state with any of these modes, but by geometric frustration, there are constraints on what can actually form. So there's a whole bunch of different compromise structures. I would speculate that this is why liquid crystals have so many different phases, because there's lots of different possible compromises among these. And then I'm suggesting that there can be similar considerations for the elasticity of the membranes, that I like to think in terms of the curvature sum and the curvature difference, rather than mean Gaussian curvature. And maybe those things might also form spontaneously. All right, with that, I'll close and I think.
We had some discussion and we're kind of out of time, but maybe quickly.
I just wanted to thank you for a really clear and accessible talk. This is so much better than reading a liquid crystal textbook. So thank you.
Unless it's my liquid crystal textbook.
I struggled out a lot of reading these parts. It wasn't yours, but what I really like, of course, is one model framework that applies liquid crystals into membranes. And I was wondering to sort of so first to understand correctly, the existing way of thinking about liquid crystals, is it indeed difficult to translate that to membranes? I mean, I could imagine if you're trying to deal with the delta modes in say like a thin 2-dimensional membranes, you have to then take the surface of a thin object to begin with. Now you're starting to deal with molecular scales, and you can't really start approximating the vector field anymore.
No, people have done this kind of translation before. That's not new. And so the same people who like thinking about saddle splay as a total divergence, they also like thinking about Gaussian curvature as something that has constraints on overall space. And so, those two things map onto each other. And so there is a long-standing literature about that. And I'm suggesting making the connection in terms of all bulk rather than bulk and.
I suggest we stop in here because we interest the time, but Jonathan is in here in the upstairs, right? So, yeah. Well,
Great,
thank you again.
Thanks for the selection. Yeah.
So I. Friday. So today's even
easier.
Yeah.
Just.
Otherwise, we can always.
Because then there is no. Or it's guaranteed to be something related to.
So.
Because I just, if I knew more about.
I'm gonna go to church for lunch.
Different for.
Oh, yeah, I had lots of. No, I don't want you to feel like you have to be our like super emergency here. We can always take a call.
Yes. Oh my God.
All right, thank you so much.
Oh, thanks for you. So what afternoon? Before I need. And I have a meeting.
Oh,
so maybe after.
So the day is lunch.
Lunch, yes. I'm down to
So maybe I could do some.
So you know, Marco and I.
Little workshop, Tyler, Kansas.
I have still not been to that part.
Oh,
Edinburgh?
I have to find a reason to visit.
yeah.
It rains all the time.
You know, not like I'm sure what's up with.
So I say there's always one time stuff. The exception of anyone right. So. Usual.
I believe.
Yeah, well, so
Actually, we're gonna talk after lunch, but it's not today.
Yeah, shall we do lunch?
Yeah, we're gonna go to lunch. We're gonna go back to church.
Yeah,
You know, there is around the corner.
No, touch this.
You want actual hot?
Yeah, I
Okay.
want, I found it for 2 months on the sandwiches and.
It's right off the story.
Do you mind if I join you?
What did I do?
Oh, I found it.
Oh. Sure.
Yeah.
It's a nice start.
Yeah.
Is it literally?
Yes.
Yeah.
Wonderful talk.
Yes, because so clear, I think my students was
I mean, it's so straightforward, after, looking at you, every time, a posteriori straightforward. It's new structure me what was supposed to be years. I think I'll still stay. Probably was because of the end, because we had this one in play maybe regulations, you know, the display Christian value, and then everything should be from way to this. I'm just speculation. Right, yes. If you hear about ramifications, then surface terms got it. And so the flow of the ramifications are expressed in terms of three combination terms. Not four. And so if they're over like solving differential equations, you know, like being and so that's complicated. And then the third story is Frederick's conjecture. The Frederick conjecture, the only of the third reaching is one down. Combination.